Hi, good morning, good afternoon, good evening, wherever you are and listening into this presentation. My name is Dibyendu, and today I'm going to talk about a deep learning based technique for approximate graph coloring for register allocation. This work was done along with my colleagues Shahid and Venkat. So first of all, a brief look at the agenda. We'll look at some of the basic concepts and the motivation of our work, then on to our deep learning method using LSTM or long short-term memory. We'll try to compare our method with LLVM's very popular greedy register allocator and look at some results, conclusion, and future work. So what is graph coloring? Many of you already are familiar with this. It's an important problem, in computer science as well as in other disciplines with numerous applications. At a very broad level, a graph coloring is nothing else but the assignment of colors to nodes of a graph such that two adjacent nodes cannot have the same color. In general, this problem is NP hard, and the chromatic number of a graph is usually defined as the minimal number of colors for which such an assignment is possible, such that no two nodes connected by an edge have the same color. Usually it's solved using heuristics, and there are various techniques that have been developed over the years, improvement of the heuristics, etc., etc. In the LLVM compiler, we use what is called as a greedy register allocator, which uses some version of this kind of a graph coloring mechanism. For the example in the figure that has been put up here, you can see that there are 6 vertices, and this graph can be colored using 3 colors, and so the chromatic number of this graph is 3. Looking at the register allocation problem, firstly, this problem was looked at as a graph coloring problem first by Chaitin way back in the early 1980s. And this is an important problem, actually one of the very important problems of an optimizing compiler, where given that we have quite a bit of variables that are accessed in your program or your function, that we need to assign the fewest or the minimal number of registers to these variables such that we don't need to go to memory and back. So for that purpose, most of these solutions build what is known as the interference graph. And to build an interference graph, we can take something like an intermediate form or a machine intermediate form, as in LLVM IR or MIR as we know it, on the left hand side, and we look at what are called as the live ranges of variables. So for this particular example in the figure shown, let's say if you look at G, right, it gets assigned here in the first place, and then it gets used in the third line, but after that there are no uses of G. So you can consider that the live range of G runs from the first instruction to the third instruction, and while it runs from the first and third instruction, it also actually interferes or are active at the same time along with other live ranges, which are mainly from H and K. So if you see in the diagram on the right hand side, the node G does have 3 edges, one going to H, which it interferes with, one going to K, which it interferes with, and J, which is actually not assigned here, but is considered as live in, that is, it has been live from the start itself. So you'll have these 3 edges from G going to all these different nodes. Now, what is the motivation for a deep learning based register allocation algorithm? One of the major motivations is a register allocation algorithm in a compiler actually has a lot of heuristics and lots of tuning that is built over the years. And if you are part of a compiler team, you know that maintaining and building upon these heuristics is very, very non-trivial and difficult. Sometimes if you change a heuristic here and there, you'll see a lot of ups and downs when you try to run performance on various benchmarks. And the reason is not known or understood very well because these heuristics have an interplay with itself, with the other parts of the compiler, and so on and so forth. So the idea is to see that whether we can build, at least for initial part, a simple deep learning model that can color graphs and can be used for register allocation. One of the motivations, as I said, is we can do away with all this special heuristics and tuning which only a few compiler engineers understand well. So what we try to do in this work is we try to build an LSTM based model, which is basically a special version of a recurrent neural network. And we experiment with some popular graphs. And then we also experiment with some interference graphs that we have generated from the LLVM's register allocator. And we see how we perform on these various graphs by using our deep learning model. So modeling graph coloring using LSTM. So while there are other techniques which I'll not go into in this particular talk, like a reinforcement learning based method or graph neural network based method, in our opinion, we thought modeling this as a sequence to sequence translation via LSTMs looks very natural. Because what we can do is we visualize the interference graph as a sequence of nodes with certain characteristics. And then we feed it to our deep learning model or network. And the output is again a sequence of colors for each of these nodes. So, you know that in machine learning or in the NLP space, a sequence to sequence translation is very popular for machine translation from one language to another. And so we just borrow from that technique and we try to model the graph coloring problem as a sequence to sequence translation. Now, as I already said, people have tried to model it using graph neural network, people have tried to model it using reinforcement learning, but we think that this is a very natural way of looking at the problem and actually is a very simple way in which we can encode and color graphs. So what is our input sequence? So our input sequence to a recurrent neural network is a sequence of the nodes of the graph, because we have to somehow encode our graph in a form such that the recurrent neural network can understand what it is. And so each item of the input sequence is an encoding of the adjacency vector of that vertex. So you know that from the adjacency matrix, we can take one row for that vector, and we just encode that sequence of ones and zeros as an input for that vertex. And the sequence length for the recurrent neural network is nothing else but the number of nodes of the graph. So let's say if you have a 20-node interference graph, you can then have a 20-node sequence for a recurrent neural network. And what you can do is each of these sequence element is nothing else but the encoding of an adjacency vector of that node. Similarly, the output sequence, which is of the same length as the input sequence, is nothing else but an assignment of color to that node. And the interesting part is because the graphs can vary in size and the recurrent neural network has to be constrained to a certain size, what we try to do is we currently in this particular work restrict ourselves to less than equal to 100 nodes. So a graph can have up to 100 nodes and we try to color it using our algorithm. Now there's also a reason for doing this. What we have observed, especially using SPEC benchmarks and other benchmarks in the compilers, is usually the graph coloring in interference graph for a function doesn't usually exceed 100 nodes. Obviously, there will be cases where there are more than 100 nodes, and we will probably give a brief about how we can handle them. But at this point of time, we think, or we have observed that a large number of functions have interference graphs having less than equal to 100 nodes. So the interesting part is once we try to color our interference graph using this kind of an LSTM based recurrent neural network, there are certain constraints that come with it. One of them is it may happen that adjacent nodes can carry the same color. But this kind of constraint is very difficult to build into LSTM today. So as a result of that, we'll see later in the slides that we actually also add a special pass after our deep learning algorithm called a color correction algorithm or a color correction pass. So as a result, we call our overall algorithm as a kind of a hybrid or approximate algorithm because we have initially a deep learning algorithm creating some amount of coloring, and then we add a color correction phase to that coloring. So other point is we need to train this model using a large number of graphs, right? So in order to train this model using a large number of graphs, we currently use random graphs, and we try to perfectly color this random graphs using a perfect coloring technique. And the perfect coloring technique is usually very time consuming, especially for large graphs. But since this is an offline mechanism, I think we can absorb this kind of time. So now if you look at the specifics of our model consists of 3 stacked layers of LSTM, followed by a fully connected or dense layer and a recurrent linear unit at the end. So for the figure, what you see here shows an unrolled LSTM, which means that the sequence or the time series of the LSTM is shown as unrolled version, as in LSTM 10, LSTM 11, LSTM 1n-1 are nothing else but the unrolled sequence of the LSTM 0, and similarly for layer 1 and layer 2. The input, as you can see, as I said earlier, is just the adjacency matrix of the graph, but we take each row as its adjacency vector and then push it into the graph. And the output, as you can see, is a sequence of color nodes starting from 0 to n-1. So how do you train the model? So the aim is to apply this model for moderate sized graphs, as I said, a few hundred nodes, but currently we restrict it to 100 nodes. And we see that many interference graphs in LLVM's register allocator for SPEC CPU 2017 are of similar size. So what we use supervised training by generating random graphs and coloring them optimally. We use a package called Naughty. So what Naughty can do is it can generate random graphs up to 100 nodes of varying sparsity, from being very sparse to very dense, and then color them optimally and generate the color assignments for these nodes. And what we have done is we have generated about 10,000 samples for training, which are all random graphs of varying sparsity. And what we do is to encode the adjacency matrix, we actually use 128 bits or 2 long ends for each adjacency vector. Okay. So one sample of the input and output sequence for the training looks like this. As you can see that if we have 100 max of 100 nodes in the graph, we'll have first 64 bits and the second 64 bits. This in totality will encode one adjacency row, right? And then similarly for the other adjacency rows till you go up to row 100. Now, there may be various cases where the graphs are much lower in size, in which case we will do zero padding for this kind of nodes. Though the model usually is trained for a large number of epochs, but what we see is after about 100 epochs or so, we get a fairly good training error value, and we don't want to overfit further, which is a good thing. So what about the inference part of it? For the inference part also, we use a very similar mechanism. For the input, we again provide the adjacency vector for the graph we want to infer the coloring, but the exact colors of the nodes associated need not be provided because we don't need them. That's being output by our LSTM. However, there's a big catch with the inference input, big output, sorry. The color assignment may be invalid. And as I said, the color assignment may be invalid because we cannot encode constraints in LSTM that adjacent nodes cannot have the same color. Because of this, we may get situations, or we will definitely get situations where the adjacent nodes are colored using the same color. And our solution for this is use a postpass called color correction to restore the validity of the color assignment. And as a result, it may need colors additional to the ones which you have used for your LSTM based coloring. So just to give you an example, this is a famous graph used in literature for graph coloring called the forest fire graph. It has a chromatic number of 5. But when we pass this through our model and try to infer, the LSTM based model colors it with 4 colors. And you can see the colors are C1, C2, C3, and C4. And then we see that there are 2 invalid edges. The invalid edges are 2 to 3 because both of them are assigned color 3, right? And then the invalid edge is between 1 and 5 because both have been assigned color 2. Okay. Now, for this, what we need to do is use this postpass correction algorithm. And then what we can see is that V5 here in this particular case can reuse the color C3, right? Because if you can see its adjacent nodes carry color C1 and C2, so it can actually use C3. So it can just reuse the C3 so the number of colors don't increase. But when we come to the edge 2 to 3, we see that this cannot be colored using any of the existing colors because the adjacent nodes all use up the palette of colors that we have. So we have to actually need to add an extra color for this particular case. So finally, we will land up with 5 colors for the forest fire graph. In addition to this, we have done inference performance on some other popular graphs, which we will talk about now. There are also some additional information in the paper, which you can look at. So one of the very well-known graphs, once again studied in the graph coloring literature, is called the karate graph, and it has a chromatic number of 5. So our LSTM uses 4 colors, right? But as a result of using 4 colors, we land up with 23 invalid edges out of 79 edges, which is about 30% of the edges that we have. And on applying color correction, we see that we use only 1 extra color. And then we actually finally, at the end of the day, manage to color it using the chromatic number of the graph. That is, we don't exceed the chromatic number of the graph, which is great news. Similarly, on the Baidu graph, which you see here, the LSTM uses 3 colors, and we have 35 out of 90 edges being invalid, which is about 38% of the edges. But in this, we are unable to reach an optimal colors, which is 3 in this case. But after applying color correction, we see that we are able to color it with 4 colors. And that's actually today one of the best heuristics that is applied for graph coloring. Also colors the Baidu graph using 4 colors. So now on to the comparison between our model versus what we are seeing in the LLVM's greedy register allocator. So just a very brief overview of the greedy register allocator before we dive into the details. If you look at LLVM's GRA, it has the following passes. It does a live interval analysis. As you know, we showed you in one of the earlier slides that we have to compute the live ranges of variables from the interference graph. And then there is something called a spill weight calculation, which means that if you are unable to keep your variable in a register and you have to put it into memory, then what is the cost of really the spilling? Now, this cost may be high or low depending how the usage is. And then we do a priority queue construction, which basically prioritizes these live ranges based on the spill weight. Sorry. Then you finally do some amount of register assignment. And after doing register assignment, if you see that you cannot accommodate all your live ranges in the registers, you start doing eviction, which means that you need to evict or spill certain live ranges onto the memory. And then in some cases, actually, you can still avoid doing that by splitting the live ranges. And if you are still unable to cover for all your registers by that mechanism, you finally need to split. So this is how the entire flow looks like in the LLVM's grid register allocator. Interestingly, the LLVM's GRA mechanism doesn't build the interference graph explicitly. The live ranges are provided, and all the subsequent steps are created from those live ranges without creating an actual interference graph. So what we did in order to do the comparison with LLVM's GRA is we tapped into the pass. We tapped into the pass of live interval analysis, and at the end of the pass, we actually create an explicit interference graph because for our DL-based mechanism, we require that interference graph. So what we do is we collected the interference graph for a large number of functions of 5 to 6 SPEC CPU benchmarks, and we ignored those functions which have more than 100 nodes interference graph for the time being. It's not a large number, it's fairly small. And then in order to do a fair comparison, we also collect the exact register count of each function of these SPEC CPU benchmarks after actual code gets generated. So what we do is we finally do a comparison between the actual number of registers that LLVM's GRA used after spilling, after everything, versus what would have been the number if we would have used our DL-based register allocator. Okay. So just to give you a comparison, we'll show you only two of the benchmarks. One of them is Leela, and the other is from MCF. The left one is from MCF, and as you can see, we have collected the register usage from LLVM's GRA and what would have happened if we would have done the register allocation via our mechanism. So as you can see, the LLVM's register alloc finally allocates from all these functions 262 registers, or 262 different kinds of registers, 262 colors totally. So for each of these functions, as you can see, switch arcs takes 17 registers, replace weaker arcs takes 16 registers, and so on and so forth. So using the same interference graph that LLVM's GRA actually doesn't build but uses implicitly, we see that before correction, which in general, our mechanism is slightly aggressive there, we use about 174, which is like much lower than this. But obviously, this is not color corrected, so this will have invalid coloring. So after the coloring, we see that we are at 257. So actually slightly better than LLVM's GRA at this point of time for MCF. Leela is on the right-hand side. We don't show all the functions from Leela, but once again, if you look at it, the number is 732. Before correction, we are 500, and after correction, we are 750. So as you can see, this simple model of an LSTM-based mechanism followed by color correction can already provide or seems very, very promising with respect to number of registers that the LLVM's GRA is using today. So based on this, we are proposing a plausible setup that can be utilized. It's not something we have encoded in LLVM code yet or even done a full-fledged design. But assume that we do the live interval analysis. The current thought process is we can actually do both the mechanisms and pick the best of the two. That is, we feed the live interval analysis to the standard spill weight, priority, register assignment, eviction, spill, split, etc., etc. Or we can do a DL-based allocation based on this interference graph. And if the number is, the number of registers required is higher than the number of registers available, we can again go through all these phases we see on the right-hand side, right? And then choose which one is better of the two, right? So if the GRA is better, what we do is we can input that information into a training database and train our model further so that it can do better for those kind of cases. So finally, coming to the last slide, in this talk, we have given you a very preliminary and exploratory outlook for the work we have done to see whether an LSTM-based solution is feasible for something as important as a graph coloring register allocation. Our initial experiments with some very popular graphs, as well as graphs from literature, as well as graphs from the LLVM's grid register allocator for SPEC CPU 2017, which we collected on our own, looks very, very promising. As I told you at the very start of the talk that there are other solutions from Baidu using reinforcement learning, but it is very costly in terms of training. And the algorithm is also much, much more complicated than the algorithm that we have proposed here. And there is another work using graph neural networks, but that is not for color assignment. It is mainly meant for kind of finding a chromatic number. So, looking at it, we can do further work on this. One of them is to see whether a different sequence, like when we input our original graph into the LSTM, we really don't bother over the sequence in which we are sending the nodes, but we can actually look at a different sequence like a topo sorted order or a DFS order or a BFS order to see whether that order makes some difference in terms of the correctness, because even after the DL algorithm gets done, we still see in some cases high invalid edges, which we definitely like to reduce. We can also experiment with newer LSTMs like attention or transformer. Most likely they may get better results than what we have here. And the final point is we actually trained our entire algorithm using random graphs, which we generated through the package called Naughty. But you can actually train it on graphs generated from LLVM itself or from GCC or from ICC or things like that. And you can build a much more focused model for your particular compiler, because that may train much better than using random graphs and training on them. So that's, in a nutshell, is what we have done as a part of this work, and hope you have enjoyed it, and I'm open to questions and suggestions. Thank you.